Sorry. So today I'm going to explain a topic somehow related to what I discussed before, and actually it's a piece of the B theory announced at the very beginning in this course. Namely, I am going to explain algebraic geometry and differential graded algebras that are behind the n equals 1. No, it's not. It's not here. That are behind n equals 1.
So, this is outside of the rim.
Still outside.
Yeah.
Okay. Is it
still outside?
Let me see how. Now I see. Okay. M equals 1. E.
Oh.
So
it's outside, but in a different direction. But okay, I think we understood.
No, but see, I need to make it properly.
Oh, right.
Yeah.
Yeah.
Okay. N equals 1, D equals 10. Super Yang-Mills. So the idea is so-called pure spinor approach. So I'll discuss supersymmetry here. So the idea is a pure spinor approach. But I'm going to treat it in terms of algebraic geometry. And what is also interesting is the structure of supersymmetry there. What is interesting is that supersymmetry of this n equals 1, d equals 10 super Yang-Mills is realized. This is realized on shell. By supersymmetry on shell, we mean the following. We mean, so for any symmetry that is realized on shell, we mean the following. It's a map from the, okay, let me put it in the form that you know, namely in terms of Batarin-Minkowski action. So let me recall that ordinary symmetry is when you have an action plus you have ghosts. Plus you have the algebra. So it happens when you have such structure with one subscript that solves the master equation.
Too many F's.
Sorry?
Too many F's.
Sorry. We may speak about on-shell realization of the symmetry. if there is additional term with some bivector such that this solves the master equation. Here the term pi, So if this term pi is absent, we speak about classical realization. If this term pi is present, then we have the following. The commutator of the vector fields plus on bracket of S and PA. So this is a vector, so I can put here I. So since this term is proportional to the S, we say that vector fields of the symmetry are closed, so-called on-shell. And it is known, so people constructed such action. And this action is raised f by f plus gauged fermion called Luina. So this is a standard notation in quantum field theory. People check that this term has this supersymmetry on shell. So I'll explain how it happens in terms of so-called pure spinor approach. And moreover, this pure spinor approach actually leads to the problem of Berkovits superparticle, etc. So, main claim is that super Young-Mills is an effective theory. Namely, it turns out that there is differential graded algebra. So this theory has a differential. Also, it has a Lie multiplication that I'll call M2, such as we have DTL. In this case, we can write, you will see, the action in the form. So it is our well-known BF action, which is a BF theory. Also, we will see that this BF theory is classical supersymmetric. You see, in this case, maybe it's better to write it not B, but A. So this A is not the gauge field. And in this case, okay, so I prefer this notation. So we will have BF plus similar structure. I'll call it capital Gauss. Plus such terms with no pi. We will show, so the plan is to say that field Q that is here is actually a sum of two terms, Q1 plus Q2. Therefore, we can go to cohomology of Q1. And I'll show several things. First, I'll explain that what you would like to call physical fields are cohomologies. So we used that cohomologies are finite dimension. In this case, cohomologies are fields. So we will have induced action. And this induced action would not be of the BF form. There will be higher operation. And that's why it will be super Young-Mills. Because as we know, super Young-Mills has also quartic term. So it's not of this form. Moreover, when we do induction, we are going to cohomology of Q1. We also induce something here. So not only we restrict this term to cohomology, we also have induction. And in this induction, we will get terms that are quadratic in psi star. And last thing that I'd like to show is that if we just go to cohomology, we will still have a theory of the form star field times some vector field. It will be a vector field. We will have to apply another procedure called potentiation. Namely, or I call it Z2 reduction. So Z2 reduction.
So that is also outside of the boundary.
Okay.
Mhm.
So we will come to this. Okay. Now I need to explain what is Z2 reduction. Imagine that you have a solution to BV equation that is of the form I star I BI of phi. Now suppose there is a BV form such that vector field is potential. Then one can show that S tilde of phi solves UV equation for BV form or symplectic. The well-known example of such reduction is where you start with a standard action. So this B, so example,
Sorry, the S tilde is basically connected to the vector field V, right?
yes,
Okay.
the potential vector field.
Okay, but it's S tilde because it's just out of the bounds. Okay.
Actually, because this is S, this is a vector field on the space,
Okay. Okay. Thanks.
and this is a function.
Mm-hmm. Thank you.
So it is Z2 reduction because here the BV space is the cotangent bundle to the space of field. And here the BV space is the base of this cotangent bundle itself. So example. And here we consider integral over odd dimensional space. We take as a BV, as a form that would be BV here, the integral over odd dimensional space of trace delta A, delta A. Since X is odd dimensional, this is odd. Here we have a vector field. It's interesting that this vector field is potential with respect to this bracket. So here I write B, I can all equally write it as A star. It is the same. Now I am getting the S tilde coming from exponentiating this formula. 1/2 ADA plus 1/3 AQ, and here we have 20. So 1/2 comes from the integration of linear thing, and 1/3 comes from the integration of quadratic term. Sorry, I have a misprint here. No 1/3. So up to the constant, we get the well-known 2/3 in the action. So that's how it's. So that it's a form in which we know it. So this is Z2 projection. So this is example of Z2 projection. Okay.
Oh,
Yes.
oh, it comes from the transitions coming from BF theory, like from first order formalism.
It's not integrating out. It's a thing that happens. I would not say very rarely. That's very specific procedure. So you can write many BV actions. Just imagine that it is vector field coming from the vector field. It could have a function, vector field, something else.
Right.
No, I think, yeah, I have some questions. So I guess for BF theory, it's not quite clear whether this omega which uses just A's has any meaning. At least classically it doesn't, right? You're not using it.
You want to when you say it doesn't have meaning, what do you mean? You mean
Well, there are two symplectic structures. One is D star DA and the other is DA DA. So
yes.
in BF theory, you are using only this DA star DA. But on the other hand, it somehow secretly appears in quantization in this second one of oh, sorry, I'm thinking about two-dimensional BF theory, that it secretly appears
No,
there.
I specifically wrote here odd space.
Yes.
So we use a symplectic form to go from vector space to the dual space.
So first we work with the space that has a canonical symplectic form, and here we impose additional requirement, and this additional requirement is that vector field is symplectic.
Yeah. No, it is.
So it has a Hamiltonian or potential. It depends how would you like to call it.
Yes. No, just some special package here. So I mean, abstractizing from the sort of field theory setting, it's you have T star M, where M itself is symplectic. So you have different symplectic forms to choose from on T star M. And you have some vector field on M, which is Hamiltonian with respect to the symplectic form on M, but you also have its lift to T star M.
So any vector field, so this is a Hamiltonian for a vector field on so phi star vi of phi
Mhm.
may be considered okay.
I think it's clear what the construction is clear, but it's also mysterious because I mean there's no equivalence between those theories.
There is, it's of course no equivalence. These two theories are different.
Mhm.
They are completely different.
Mhm. Oh, actually, maybe not completely different because at least on the
Okay,
level of
okay, I'll say not. You see, it's wrong to say they are completely different. However, the space on which you have this series is different.
no, on the level of Feynman diagrams, it seems that yeah, like tree and one loop diagrams are more or less the same, and higher diagrams exist in Chern-Simons, but not in BF.
Yes, and let me say that many years ago, I had kind of a conjecture, and this conjecture is, so these are classical theories that are relayed by this Z2 reduction. So the question is there any relation between the, so for classical actions, it's clear what's going on. The question is, what happens in quantum case? So here, as Pavel said, we have only one loop, okay? While in the theory for S tilde, we have many loops. So here, so there are two procedures. I'd like to write them in terms of the conjectural diagram. So we have a theory, and here we have quantization. And between this, and suppose we have another theory, and here we have Z2 projection. Sorry, I meant another thing, not quantization. So suppose we have a theory, and we can go to cohomology of Q, and we have induced theory. Then we have Z2 projection, and we get theory tilde. So if here we have a vector field, here we also have a vector field. I call it vector field theory or just element field. So we can have Z2 projection here. possible to go to cohomologies of Q here. The question is how they are related classically and quantum and not quantum. So this is a purely theoretical question, and there are examples. So the most striking example is, suppose we know BF theory of this type in odd dimension. So we have Z2 projection this way. It's interesting to see how loops are related and what happens with the relation between loops if we go this way and this way.
So, well, it seems that they're not related beyond one loop.
Yes, but I don't think that they are absolutely irrelated. Because you may consider the equation of quantization, that is a equation of deformation of solution to master equation. Of course, they are not equal, but I strongly suspect that there is, and it's a conjecture, that there is a kind of transformation that relates their quantization. So if we quantize in terms of graphs, of course, in one case there is only one graph, in other case there are many graphs.
Mm-hmm.
So in S theory you have only one loop, and here we have many things. So it's interesting to see what happens, because we have two theories here. And in most cases, so we have theories that seem to agree on classical level. So what does that mean when we say that they have different quantizations? So it's an open problem. I just want to show that there is such an intriguing question. What is going on?
It is very intriguing, but and it doesn't sound very plausible that you can somehow recover the, I don't know, very complicated answers for the higher loop diagrams in Chern-Simons, which are whatever, some configuration space integrals, which are, I don't know, complicated to compute.
Yes, but do we mean that here we have two different quantizations?
Yes.
Okay.
Well, yeah, I'd guess so.
So if we, but in many cases, people think that quantization is unique. So it's unique up to something.
I think also classically it's a bit different. I mean, even trees, they're sort of unoriented in one case and oriented in the other case.
Yes, but if you do this thing,
mm-hmm.
and then come here, on the classical level, this diagram is commuted, or seems to be commuted.
Mm-hmm.
So interesting question is, in general, when you go to cohomology, what happens to the BV form?
Mhm.
If BV form is a constant, it's clear. If BV form is not a constant, it is kind of a theory called the induction of the theory with cyclic structure. Okay, so people call it cyclic structure because of the following reason. So operations of L infinity are many inputs, one output. If you have omega BV that is constant, it means that you have omega BV of this type.
Yes.
So from the vertex that has inputs and one output, you can form such a vertex.
Mhm.
Then the condition of cyclicity is that here you have symmetry among inputs.
Mhm.
So if such thing happens, we call L infinity having a cyclic structure,
Mhm.
the symmetry. And this cyclicity is exactly the condition that vector field is potential. And here we have something that has only input and no outputs. So that's why this is a function.
Mhm.
Now it's an interesting question. What happens with cyclicity when you are now? Now just imagine that omega BV is not a constant.
Mhm.
After all, there is a symmetry of L infinity. That is diffeomorphism of the base.
Mhm.
So omega BV may be constant in one set of coordinates. In another set of coordinates, it should have some other input.
Mhm. But these inputs, they are different somehow because omega is a two form, right? So the symmetry condition are different for a pair of inputs.
Yes. Yes, in this sense, there is no, okay, you are right. So that's why I write it this way. And as far as I remember, cyclicity means that this thing is symmetric. So it's a generalized cyclicity. So the fact that vector field preserves omega comes from this diagram and maybe also diagram entering that way. So it's an interesting question. There are not so many papers on it. So
Mhm.
I can also write down this.
That actually should not be a part of the equation
So
because
let us,
you're substituting the vector field into the differential form. So in the sort of dx slot, not into the x slot.
maybe, so let us see. We would like to say that vector field is symplectic, okay?
Yes, yes, yes.
So what do we mean? So it's not a condition of just substitution.
Well, we can say either that it's symplectic or that it is Hamiltonian, but yeah.
I say symplectic.
Yes.
So I thought that it is a condition like this.
Yes, yes, right.
It's not a condition that IV. So just imagine that this omega is constant. So let us try to do this computation.
No, maybe you're right. So let's see.
So after all, you see, it's interestingly, it's a fundamental question in the theory of L-infinity algebra. So let us do it. So, good. So let us discuss this issue in some detail. So let us compute. What this could be. So actually, we have to decompose. So what do we do? So first thing is that we put vector field here.
But
Okay.
I mean, by the way, so still LV of omega is just D of IV of omega. So you are substituting V into omega. And then, okay, then you take the RAM.
So let us L. Okay. Okay. Maybe I'm wrong, but let us get it right. So we are looking for this equation.
Yes.
So
Cardan's lemma.
IV plus IVD.
Yeah, and the second term vanishes.
So we have D. So maybe you are right. DIV omega equals to 0. So what this means? It means so for constant omega. For constant omega, it means exactly what I wrote about. But now consider that omega is not constant. Okay. So I have to take V omega. It has this d phi I input. And this has phi input. So omega is a function of phi,
Mhm.
d phi I. So it has this thing.
Yeah.
Now we are taking d.
Mhm.
So maybe you are right.
Mhm.
So there are d's acting here.
Mhm.
So there is a symmetry between this input and this input, right?
Mhm. Yes. Yeah.
But d can also act here.
Yeah. Mhm.
So we have to also include symmetry of this.
Mhm.
So it's more complicated condition.
No, but I think it just is this the symmetry in all the inputs, isn't it?
Yes, I also think so.
Mhm.
But I thought that's what I said.
No, the question was about the second type of diagrams, whether they appear or not, and it seems that they don't appear.
Ah, that vector field doesn't appear here.
Mhm.
Yes. Okay. Okay.
Mhm.
Okay. Yes, you are right. So symmetry of all type of input.
Mhm.
Ah, you are right.
Mhm.
So this is what we can call infinity cyclicity.
Mhm.
That you're making operations this way. Yes. So there are two things that I have not studied, but they probably could be studied. Namely, this is a quadratic equation,
Mhm.
this cyclicity. So the question is how to write PV structure, PV equation. And also how to write quantum version. And then the second question is what happens when we take PV integral? In particular, what happens if we go to cohomology? So I saw some papers on this stuff. But not so many, and they came not from physical side. So in the simplest case, where omega is, if we work in the coordinate system, where omega is constant, maybe you may say that there is always such a system.
Oh, sorry, what did you say?
So just imagine that such omega exists. and non-degenerate. There is a coordinate system where it could be taken to be a constant.
Yes. Yes.
Then you may say, let us work in this coordinate system. But still there are two things. First thing is this thing that I called Z2 projection. Unfortunately, it doesn't have a standard name in the literature. And second thing, it is BV integral. And the particular case of BV integral, it's a reduction to cohomology.
So do you actually need omega is a constant? You just have a condition of omega is closed.
Yes, but in order to simplify consideration, I would like to treat it in the case where omega is constant. So still, there is an interesting diagram. So we have a theory. We can take a Z2 projection with tilde. And here we have BV integral. Or we can first have BV integral induced. So most probably we have two arrows. So on the classical level, for the constant omega, they seem to have to give the same theory. Interesting question is, of course, what happens on the quantum level? Because we potentially have two ways of quantization of the classical theory here. So suppose we have this theory and imagine that we quantize it. Then we can go this way or that way. So it is an interesting question in quantum field theory case. However, it's a pretty well-defined mathematical question.
So it's probably kind of what one actually has is not this kind of procedure of halving, but the procedure of doubling, which is very straightforward, which is just taking the cotangent bundle of a manifold, and if you have a vector field, well, it's clear how it works in the opposite direction. And on the level of quantization, this doubling, it will just forget some information, like higher loops.
So you propose, so you are saying the following. Suppose we start from this. You say that we can always get here.
Yes. It's getting a vector field from a potential.
Getting a vector field from a potential, yes. But but when we get here, we also remember the symplectic form that we have here.
Now, in theory non-twiddle, we sort of we get the vector field and then we can ignore the original symplectic form on the.
But in order to have kind of equivalence, we should get here remembering this symplectic form. And then when we go down, we should also see what happens with this symplectic form. So if we just go to vector field
Mhm.
from the potential, forgetting symplectic form, of course we are losing the data, namely this symplectic form.
Mhm.
But let us keep it. So that it means that we are considering the space of pairs,
Mhm.
namely vector field and symplectic form.
Mhm.
And since this is a quadratic equation, I hope, I have not done this,
Mhm.
I hope that this could be made an equivalence if we consider theory with symplectic form as an extra data. Because this can be.
Mhm. Mhm.
Yes?
No, I'm not sure how to, well, let's say in three-dimensional BF theory. So that's your example where T is, I don't know, odd dimensional BF theory. So how, I mean, a BV package is, you know, here the canonical symplectic form, which is like DA star DA, and the action. So, or yeah, the action. So how on the field theory, in the field theory language, what is the meaning of the second symplectic form there?
So there is a form delta B, delta A,
Yes.
integral,
Yes.
and here canonical bracket.
That's the canonical symplectic form, yes.
So this is canonical symplectic.
Mhm.
However, if X is odd,
Mhm.
if X is odd,
Mhm.
and algebra has invariant quadratic form, like it happens, has invariant non-degenerate, like it happens with the algebras, with the simple Lie algebra, with the semi-simple, with the reductive, okay?
Mhm. Mhm.
That I'll denote like this,
Mhm.
or I'll call it trace.
Mhm.
We may have another thing. Just compare, these two things are different.
No, of course, of course.
Delta B, delta A. Here we have delta A, delta.
Of course, I just don't know what it means to, what this object means in field theory. I mean, it's not, I don't know, it's not an observable. It's what sort of an enrichment of the field theory is it?
So I don't quite know
Mhm.
what it is.
Mhm.
However, what I know is that there are equations.
Mhm. Yes. Yes.
And and these equations are equations among two operations.
Mhm.
You see, like so. And here, it's a kind of canonical substitution of something into something.
Mhm.
That's why I have once again a conjecture
Mhm.
that infinity cyclicity may be written as BV equation, as classical because it has pretty similar structure. So
Mhm.
I have not done this,
Mhm.
but I have, so that's a conjecture that this may be done. And it's kind of a good proposal, kind of a problem to do this.
So actually, I'm not sure what you're saying. So classical BV equation is something that's quadratic in V. And here you have an equation which is linear in V and linear in omega.
Yes. So I mean, of course, I mean that the space of, so here we have fields and anti-fields.
Mhm.
And here we have something extra.
Mhm.
So this most probably should be considered as a BV equation on some enriched space, not on the
Mhm.
same space.
Oh, I see. I see. I see. Mhm.
Yet I don't know how to do it. So we know it. At least I know it in this graph form,
Mhm.
or in the form LV omega equals.
Mhm.
It's a quadratic equation.
Yes.
So we know that that condition that is called invariance could be written in the BV form, right?
Mhm. Mhm.
So we know it. So somehow we have to put it together.
I see. I see.
So as far as I understand, nobody did it, and nobody considered this thing as a quantum theory. So it's an interesting question, even for a finite dimensional case.
So you would probably look for an extension of the original L-infinity algebra to some other L-infinity algebra, which sort of with additional operation or sequence of operations corresponding to omega.
Yes, exactly.
Mhm. 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 Mhm.
So here I want to say that so I call it Z2 reduction. Maybe there is a better name, but I don't know any standard name. Or you may call it infinite cyclicity.
Mhm.
Okay, it means that I just point out that there is such a structure.
Mhm.
And I just want to point out that people do not study.
Mhm.
So it's a good thing to study.
Yeah. One could call it the square root of the theory, but by the same token, like as in you get like for one loop you would get like the root of Reidemeister torsion instead of the Reidemeister torsion itself.
Okay, maybe so it's two. It has two inside. Because of this two, you may say square root.
Yes. Mhm.
So that is what I know about it, about this
Mhm.
operation.
Mhm.
Okay.
Mhm.
So now maybe we need to make a break here,
Mhm.
because the good style is to have a break each 14 minutes. Yes. So it's it's more than 1 hour. Now it's good to have a 7 minutes break. Okay.
Okay. Okay. Okay. Mhm. Mhm.
Okay.
Mhm. Mhm. Mhm.
So we are waiting for Donald.
Yeah.
Okay. So this is about this square root, as Pavel proposed, or Z2 projection that I call it. Once again, completely unexplored subject. And in particular, there is nothing about it in Cataneo's review.
Which Cataneo's review?
So he had a review on infinity structures.
Really?
Yes. Several years ago. I don't know how long. I mean, Alberto Cataneo.
Yeah,
He
yeah, no,
wrote,
sure.
I forgot how many years ago, but like 5.
Just about infinity structures. Oh, yeah, I don't remember that. Mhm.
So actually, as Pavel said, it is a kind of a new way to quantize. So go to the equations of motions that are the same in these two theories, and just keep trace of the symplectic form. So general log would say, general law would say that there should be some relations. These two things are equivalent. And that's why most probably they should descend. If this relation is natural, they should descend together. Okay, but now let me talk about very particular system. Namely, first I'll describe BF version. And then I'll do Z2 projection. So I'm going to write down now DGL. And this DGL would be, as always, supercommutative A infinity times Lie algebra. Or you may call it a Lie algebra valued function on the spectrum of this supercommutative A infinity. Actually, it would not be even A infinity. It would be, sorry, supercommutative algebra. So in the case of Chern-Simons or BF, we used to put here supercommutative differential graded. In the case of Chern-Simons, we used to put here the algebra forms on the manifold X and the ramp differential. So it's traditional. Traditional way. Now we will replace this by something and this by something. Okay? So first I will describe what would replace this omega star of X. Namely, I will consider R10 and functions on R10. Smooth. They form commutative algebra. And then I will multiply them by commutative ring. Let me explain what this ring would be. Point number one. I consider Weyl spinors in 10-dimensional Weyl spinors in 10 dimensions. The dimension is 2 to the 10 by 2 minus 1. So this is the dimension of all spinors, because this is dimension of lambda star of C5. Should I recall why spinors are these? Donald, should I recall?
Yes, please.
Okay. So spinors are representations of the algebra called Dirac algebra. I goes from 1 to D. Suppose
Clifford algebra, right?
Clifford algebra, yes. But Dirac, Maybe Clifford introduced it before. Suppose D equals to 10. Suppose D is even. So then I can change a basis in this algebra. Namely, I'll call gamma plus A minus A equal to gamma J where J goes from 1 to D over 2. So it's better to put it gamma J. So instead of D gamma J's, I have D over 2 gamma J pluses and D over 2 gamma J minuses. It's easy to check. That this thing anti-commute. We have cancellation of commutations because of the I side. And the same is true for minus. However, gamma plus J, gamma minus K anti-commutator is delta IK, delta J. Now, we consider polynomials of gamma minus, maybe on gamma pluses. They form external algebra of C D over. Because these are anti-commuting. And now gamma I acting here as a differential operators. So we represented this algebra.
I see. Thank you.
Now, Lorentz rotations being commutator symposium are acting here as differential operators. Actually, these operators are second order differential operators in general case. So each thing is something like this. And here I have commutator. Note that since I have commutator and not anti-commutator, I actually have second order, first order operators and also algebraic term. And this is a representation of the Lorentz group. Now, so these are Dirac spinors. Now we see that gametes change the number of gamma pluses by 1. It either goes down or up.
Mhm.
So lambda ij preserves number of gamma pluses moduli 2. So we can decompose here odd part and even part. And these transform under Lorentz rotations independently. These two parts are Weyl spinors. That's why the dimension of the Weyl spinors is like this.
Mhm.
What is interesting is that in dimension 10, there is an invariant just let me say, let me see how to say it. There is a pairing between, so one of them are left and right. Left and right spinors invariant under SO10. Moreover, if we take left spinor, apply gamma, it will be the right spinor. Then we take left spinor and take this pairing. This is a symmetric quadric. It's a special property of dimension 10. So it's a question of duality between representation. In particular, in the group SO4N spinors are self-dual. So dual representation to spinor is a spinor representation. So how do we easily see it? Consider very famous SO8. It has the following Dinkin diagram. So for all SO to N, we have such Dinkin diagram. So for SO8, we have this. Here we have vector left spinors and right spinors. So if we put 1 as a weight, for SO8, we have left spinors, right spinors, and vector representation. Vector representation is obviously self-dual or self-adjoint. You see, here we have the symmetry of the diagram. Because of the symmetry of the diagram, we can easily see that left are also self-adjoint and rights are also self-adjoint. However, for SO for N plus 2, the representation that is dual to left is right. So this pairing is actually a pairing between right spinors and left spinors, because they are dual to each other. So therefore there is such a pairing. So interesting thing is that one needs to check, is this quadratic form symmetric or anti-symmetric? And it turns out that that for SO8N plus 1, it is symmetric. And if I put here not 8, but 6, so what would it be? So this N could be even or odd. If N is even, then it is symmetric. If N is odd, it is anti-symmetric. So this SO8N plus 2 is symmetric. So first time it happens when N equals to 0. However, it's not an interesting case.
Why is it not interesting?
SO2.
Yes.
Everything is one-dimensional.
Yes. So it's a two-dimensional. Okay. Yes. Yes. Mm-hmm.
So you may say plus 1/2 and minus 1/2.
Mm-hmm. Mm-hmm. Okay.
And what is gamma in this case? So SO2 is not representative. So the next case is surprisingly SO10.
Mm-hmm. Mm-hmm.
So that's how we got to this 10 in this count.
Mm-hmm.
So to have wild spinners, we have SO2N to get spinors that are not self-dual, we get to the S4n plus 2. To get symmetric, we get this. So later on, I would use the standard notation and denote while spinors as lambda alpha. So convention is that I have these quadrics. Or here I put lambda and here I put lambda. And this I call gamma I quadric.
By quadric, you mean the equation that is 0, or?
Oh, at the moment, quadric is a quadratic function.
Okay.
Now, Pasha, you are right. It's interesting to see if this has any meaning. Namely, the intersection of these quadrics. And actually it does. And the meaning of it is the following. In this particular representation, we see that there is a distinguished spinor 1. So it means that set of all gamma i's acting on 1 give you 0. You may call it a vacuum. Now you may ask a question. Can a spinor be a vacuum, however, in different polarization of gamma matrices? Because you see, polarizations that I took, namely the composition, the algebra into annihilation creation operators, is kind of arbitrary.
Mm-hmm.
I could have another choice.
Yeah.
Then there would be a new vacuum.
Mm-hmm.
So then the question is, when spinor could be a vacuum in some polarization, So once again, polarization is a separation of the complexified space of gammas into positive and negative part. Or you may call it in coordinates and momenta. And answer is it could be done if and only if these conditions are satisfied. So let me leave it without a proof.
So if and only if for the spinner all those quadratic expressions vanish.
Yes.
But one can ask a similar question in other dimensions, not just 10, right? What characterizes a vacuum?
Question may be asked.
But does it mean that there are as many solutions of these equations as there are polarizations? So complex structures on R10?
Yes. Actually, in this case, the space of solutions of this equation form a line bundle, of course, over polarizations. And it is kind of instructive to compute its dimension.
So it's SO10 over U5, I see.
So it is 10 times 9 over 2 minus 25. 45 minus 25, it's 20, it's real dimension. 10 complex. And of course, it's a line bundle because we can rescale spinor. So space of solution has complex dimensional level. The dimension of spinors, so let me compute it again. So this is 32 over 2, it's 16. So we have overdetermined system of equations. Six, 16 variables, 10 equations, 11 space of solutions.
So this bundle is non-trivial.
Non-trivial.
So there's no canonical way to transition from a vacuum in one polarization to a vacuum in another polarization.
I think it has no connection.
Mhm.
No natural connection. No natural flat connection.
Oh, interesting.
You see, it comes from rotation. So you have rotation, and U5 is stabilizer.
Yes. I wonder if there's a natural projectively flat connection.
I don't know.
Mhm.
So after these preliminaries, I am coming to the space, to the ring. So here I take Weyl spinors, and here I consider them even. And these are Weyl spinors odd.
This is probably the Weyl with a Y. It's probably Hermann Weyl, not Andre Weil.
Maybe Weyl. 1 second. Okay, and then I divide it by the ideal generated by these quadrants. And then I'm doing nothing with thetas. And I multiply it by functions on R10. So at the moment, this is clearly commutative, supercommutative associative ring.
So it's surprising that we did something to one half of the spinors, but nothing to the other half.
Later on, I'll explain the algebra geometric meaning of this.
Mm-hmm.
Okay?
Mm-hmm.
Because first I'm writing a construction, and then I'll explain what will it mean.
Mm-hmm.
And then let me consider Q. It consists of two. There are two ways to write this Q.
Mm-hmm.
So let me erase this. It's a one way to write this Q. There is another way to write this Q.
Mm. Actually, what are gammas above?
The same. So gammas
Mhm.
are coefficients of the quadrant.
Mhm. Okay.
Then the alphas
Mhm.
So
Yes.
when we are writing down Q, it's very important that Q squares to 0.
Mhm.
So Q square is at the moment not trivial because this d over d theta and theta could give something.
Mhm.
It is actually
Mhm.
but this is 0 because of this quotient.
It looks a little bit like the equivariant differential.
Yes. And soon we will see its relation to equivariant differential.
Mhm.
So it's also coordinate ring for supermanifold.
It is what?
It's a ring of coordinates for supermanifold.
Yes.
It is related, and I'll explain in a second.
Yes.
Mhm.
Okay. So from the point of view of Q, if I consider this decomposition, it is clear that Q1 squares to 0 is obvious. Q2 squares to 0 is also obvious, nothing to commute. And if I commute Q1, Q2, anti-commute. I will get exactly this expression. Once again.
Mhm.
I call this representation 1 and this 2. You may say, what is the difference? Here I'd like to consider it as a single something. And here I'd like to decompose it into a sum. Okay?
Mhm.
So let me explain. Because both representations, 1 and 2, have geometrical meaning. However, these geometrical meanings are very different. Okay?
Mhm.
Let us consider representation 1. this is the left invariant vector fields on the supergroup. Terms in the bracket.
So which supergroup?
So I write superalgebra. Supersymmetries, translations. Let us check. I think it's clear that these vector fields anti-commute exactly as they should.
Yes.
So here we have the formula of this term. What is interesting? It's interesting that since these are left invariant functions, the vector fields on the supergroup. So how to get this vector field? Here you have a Lie algebra. You consider exponent, and as far as I remember, you can write down the group element. I think that if it's written in this way, then left invariant would be something like this. In this parameterization, I am not sure about if I should put it here on to the left or to the right. But it is the meaning. We already met such operators when we studied chiral fields in supersymmetry. What is interesting is that one can easily guess another set of vector fields that commute with this one. They are right invariant fields, right? And since supergroup is not commutative group, right invariant fields do not coincide with left invariant, but they commute with each other. Minus. Now, you may see that these two fields actually form representations of superalgebra, each of them, and anti-commute because of this minus sign. But they have to do it from the canonical geometrical structure, because left invariant vector fields always commute with right invariant. All right?
Mhm.
So you can do it on any Lie group. So the best known case is when I consider S3, that is SU2.
Mhm.
So you have left invariant fields and right invariant fields.
Mhm.
And if you understand S3 as quaternions
Mhm.
of the moduli 1, so it is a quaternion, 2 by 2 matrix. Then you have the rotation in alpha index and rotation B dot index.
Mhm.
And of course, these actions commute. You have SU2 from the left, SU2 from the right, all together they form S3. You see, it's S3, not S2.
Mhm.
On S2, you have only left invariant fields. On S3, you have two commuting fields, set of fields. Okay, so it was a geometrical command.
Mhm.
So from representation 1, we see that this Q commutes with the supersymmetry.
Mhm.
Given by this. Now, later on, we would like to write
So this is cut
an
off.
act.
This is cut
Ah.
off.
Okay, maybe I'll come to this later, but this is important remark. And it comes from representation 1. Now, it's interesting to study representation 2, okay?
Mhm.
Because it turns out that representation 2 also has geometric meaning. Namely, let us see the geometrical meaning of this.
Mhm.
It looks so with Q1 being this. At the
Yes,
moment,
Mhm.
oh, sorry. This complex is well known in mathematics.
Mhm.
And it is called higher torsion. So this system is interesting because here different branches of mathematics come together. Let me recall what is torsion. Okay. Suppose you have a ring. And suppose you have two modules. M1 and M2 over the ring. Naively, one can define tensor product. M1 but as people are telling us, such operation is too naive. Actually, this has to be replaced by the complex that is called Tor. Namely, you have to replace either M1 or M2 as a complex of three modules over R.
Mhm.
So C1 is a sum of several copies of R, being of course module over R.
Mhm.
So R is not the real number of the ring. Or you may say that it is so if string over a field, you can put here a vector field.
Mhm.
Okay, so it's clear. So I have this complex with differential. Then I need to study with differential d1 that clearly acts here. And this in such cohomology is called torsion. And what is interesting is that I can equally study M1 times C2 with differential D2. Should also be torsion. I can also study C1 times C2 with differential D1 plus D2. It would also be torsion. And theorem is that they are isomorphic.
Mhm.
So the isomorphism between this and this is known as a tic-tac-toe. People study it when they study equivalence of different cohomology. They have a complex with differential. They have another complex with another differential.
Mhm.
In order to prove that everything is okay, they consider the total complex and play here the game, showing that everything either goes to cohomology of D1 or to cohomology of D2.
So is it exactly the same as the left and right derived tensor products?
Yes.
Mhm.
It's derived tensor product. Standard name is torsion.
Mhm.
Because so it's torsion, I think, because it came from the ring like Zn
Mhm.
in number theory.
Mhm.
Okay, so it's known as torsion. Actually, it's derived tensor product. Now, how what we are studying is related to this.
But by the
tensor
way,
product.
yeah, maybe it's good, yeah, this example, if you take indeed Z mod n. So what happens?
No, I prefer to do it here. So
Okay. Mhm.
it is because I don't keep it. So I know that that it's how you see the torsion is a classical say, but
Okay.
you see, I need to think for an example.
Mhm.
So we need to see in our picture two modules.
Mhm.
May I just
Interesting.
ask a quick question? It might be a very stupid
Yes.
one, but it's torsion of what? I mean,
It's called torsion.
so it's not torsion of, I don't know, the naive product M1 times M2 or something, or the torsion of M1 or whatever.
No, so this thing is called. It's
Okay, it's just
a
a
definition.
name. Okay,
It's just a name.
okay.
Now let us see two modules. So module 1 would be the ring. First, the ring.
So it could be so, Donald. So maybe it comes from that example of having one entry being z, one input being z z mod n, and then it's like maybe something related to the n torsion of the second module.
Yes,
Oh, okay.
yes, but
Okay.
I think so, but I don't have. You see, I need to think how to. How to
I
put
mean,
it, so.
people usually talk about the Tor functor, and that's, I think, when you consider one input as flexible.
So it's actually derived the tensor product. So ring would be polynomials in lambda. The module M1, as you may see, would be exactly this. Now, what would be the module M2?
So we need, okay.
So it's called skyscraper.
Oh.
So why it's a module? You multiply by lambda, any polynomial here, and you take quotient by this I, and here by this I. So neither M1 nor M2 are free.
Sorry, M2 is just isomorphic to C.
Yes, but when you say that it is C, it's not here how lambda acts on it.
Yes.
So you need to say in which sense C is a module over C of lambda. So you need to put.
Well, a trivial module actually. So all the generators act by zero.
Yes, but it's still you need to say it. Actually, all lambdas acting here So actually, it is easy to construct a resolution here. A resolution is this complex of free modules. And this was done by Hilbert. So Hilbert done many things, but it's known for a long time. So when Hilbert did it, he never used Grassmann calculus. But now we can enjoy Grassmann calculus to restate it. Namely, M2 is quasi-isomorphic as a complex to polynomials in lambda and theta with differential lambda d over d theta. From this, it's clear that it is a trivial module. First, let us see that it is that there is such a isomorphism. Actually, lambda is equivalent to d of theta. So that's why all lambdas so first of all, lambda acts here, and its action is trivial. And this is called Koszul differential. Okay. Now, let us see why this is a complex of made out of free modules. It's because C of lambda theta is nothing but C of lambda plus 16 copies of C of lambda times theta alpha. But all these modules are clearly free. So that's why we actually have the sum of free modules. So putting it all together, we see that our ring together with differential is nothing but the Tor complex. So this is the geometrical meaning of Q1. Now, we still need to write down the action. Okay, so all these were just comments about what is the meaning of Q. Now, let us consider as fields A So now we are ready to write the kinetic term. Once again, this is only Q1 first piece. Then, of course, there is the interaction term. Like in Chern-Simons theory, the bracket is the bracket in the Lie algebra.
Mhm.
And here we have multiplication. And this actually works as, so this solves master equation exactly like BF theory.
Mhm.
Now, we may enjoy the symmetries of Q. So these symmetries of Q are operators that are called SR, but we would like to put them in the BV form.
Mhm.
Plus, of course, we have also translations. Let us call L I the ghost that corresponds to translations. Maybe it's not a good name for it. It should be Greek. Lambda is, okay, tau. Tau because of translations. It's not all. Because we need also to put the commutation, the commutator term.
Mhm.
Now it's all. So this is the BV action.
Mhm.
Okay?
Mhm.
Now let me remind you that epsilon are even because they are ghosts for supersymmetry, while tau is odd. And this satisfies master equation. If you look at this action, you may make a trick that is pretty similar to what we did in equivariant cohomology. Namely, we may pick up pure epsilon. and consider it as being a constant,
What do you mean pure epsilon?
pure spinor.
Ah. Mhm.
And it means that we may forget about the rest and consider this theory. You may see that Q gets modification. So here we see the theory in the epsilon background.
Mhm.
So you may either study all epsilon or fix epsilon to be something, so before, so I have only 13 minutes reasonably
Mhm.
today. So I don't want to hurry up. So I hope I put some intrigue here, yes?
Mhm.
At
Mhm.
least I think it's interesting interplay. The only question is that you may ask how Young-Mills comes out of it.
Right, but also you this Q is Q1, and you're talking about Q1 plus
No,
Q2.
total Q.
Ah, okay,
Here is total.
okay.
So actually, here we already have fields, but these fields are not fields of super Young-Mills.
Right. Well, you mentioned
So
that we need to do some induction.
yeah, we need to do not induction, but reduction.
Well, okay, to a subcomplex, or whatever you call it.
So you see, that's why I explained two forms to represent this Q,
Mm-hmm.
one way or another way, okay?
Mm-hmm.
In the representation of one way, when I do not separate Q into parts, this is very natural. This is naturally supersymmetric, but this is absolutely not clear why it has to do something with Young-Mills. So the strategy to see Young-Mills here is the following.
Sorry, Andrea, just is there should be one more there be one more term in this action in the lower part with tau?
Here,
Yes.
if epsilon are even, if I have a pure epsilon, then I can forget about the rest. I can forget about it.
Really? Okay. No, Why? So I mean, there was a term with epsilon tau, which is 0 because it's a pure spinor, but there was also a term with tau a star di a.
Yes, but I can omit it. You see, I can consider the full super algebra, or only.
Okay. Okay.
Or only pure spinors. You see, it's like in equivariant science. When you do equivariant cohomology, you restrict yourself to the abelian subgroup acting, right? So actually, I explained two games. One game would be to consider arbitrary epsilon and have these extra terms. It is interesting. Another game is to restrict to pure epsilon. It's also interesting because it resembles equivariant cohomology. Now I need to show the strategy how to get Young Mills. I could go to cohomology of Q1. So cohomology of Q1 deals only with functions of lambda and theta. So cohomology of Q1, you may expect, would be some finite dimensional space. I'll call it the space of polarizations. Actually, cohomology of Q1, okay, I need to restrict myself. So P is cohomology of, okay. Let me say that Q1 acting on just on this. Consider this. So it has finite dimensional cohomology. That is, of course, Tor. But cohomology of Q1 acting on C lambda theta I function on R10 times Li, what it is? It is Tor star times Li times function on R10. Okay? So I may call this or these polarizations. Because cohomologies are fields with value in this finite dimensional space. Why I call it polarization? Because in physics, people studied electric light. And it had a space-time dependence. And also what people call polarization. People call it polarization because originally they did not know the structure of light. Then they used polaroids and different things. They found that light has some internal structure called polarization. So this internal structure of light, besides its space-time dependence, is called polarization. So in this case, this Tor times Li is called polarization.
Mhm.
And here are fields. So what we will see is that this Tor star would give us exactly those polarizations that appear in super young mirrors.
Mhm.
You see, now my time is definitely over.
Mhm.
And so was my speed proper?
Yeah, I think
Yes.
that was very good.
Yes, yes. I think it was very good
Was
as
it
well.
understandable?
Yes,
Mhm.
yes.
Definitely so. Definitely so.
Is it clear why this thing is analog of equivariant cohomology?
More or less, yeah. I'm more puzzled by what you mean by Tor here and whether it's exactly the same Tor as what we had before, or whether, because that Tor didn't look finite dimensional.
So we will compute it and we will see that it is. And the
All right,
fact that
yeah.
it is finite dimensional is the essence of the Hilbert theory.
Mm-hmm. Mm-hmm. Yes, because previously your example of Tor was just the output of the Tor construction was this complex.
Yes. The complex.
So you're saying that the cohomology of
Cohomology.
Tor is finite dimensional. I
Cohomology.
see. Yes. Okay.
So people sometimes people rarely say Tor complex. They mostly say Tor star.
Mm-hmm.
Actually, Tor complex is infinite dimension.
Yes.
For sure.
Mm-hmm.
What's interesting is that its cohomology are finite dimension.
Yes.
So I do not want to mix everything.
Mm-hmm.
So let us consider this as the first part of my talk. Okay.
Mm-hmm. Yeah.
Mhm.
No, that sounds very good.
So I'll continue next Wednesday. So you see, I feel better.
That's
Like
very
a
good.
dog.
That's
Yeah.
very good.
And
No.
of course, we will talk on Monday. I hope so.
Okay. Excellent. Mm-hmm.
So I am very sorry for bad health condition.
No. I mean,
We're very happy to hear that you're feeling better. All right. So maybe I should stop
Okay,
recording.
thank you for coming.
mhm.
Thank you.
Well, thank you. Thank you for the lecture.
Thank you.